Okay, we're good now. All right, so again, this says gasoline contains octane, which I gave you the chemical formula for, and I say the engine of a car burns this hydrocarbon along with other hydrocarbons in the presence of oxygen to make energy to power the engine. Write the balanced chemical equation for the burning of octane in air. So these last few words here, burning of octane in air, this is indicative of a combustion reaction. So, the reactants of a combustion reaction will be a hydrocarbon. So we have octane. It burns in air. Air is oxygen, right? O2. And you need to know the products of combustion are going to be carbon dioxide and water. Okay. And so I'm tasking you with balancing this equation, right? So, one of the main things that we learn in this chapter 3 is balancing chemical equations, right? Um, why we have to balance chemical equations is we have to follow the law of conservation of mass, right? Or conservation of matter. So matter is neither created nor destroyed in a chemical reaction. So what that means is on my reactants and on my product side, I have to have the same number of every element, right? So just looking at it right off the bat, this equation is not balanced, right? If you look at the carbons on the reactant side, I have 8, whereas on the product side, I only have 1. So we need to make those numbers equal to each other. Okay, so the way that we balance chemical equations, the way that I do it is I'm gonna just erase this to clean it up a little bit. What I do is I kind of make a little T-chart and essentially what I do is I take inventory of everything that I have, right? So on my left side, I have carbon, I have hydrogen, I have oxygen. So let's count and see how many of each we have, right? So carbon, we have 8. Hydrogen, we have 18. And oxygen, we have 2, right? We go to the other side, right? We go to the right side of our arrow, which is the product side, and we count again. And I like to keep those elements in the same order so it's easy to like cross-reference those. So we start with carbon, right? We count those, we only have 1. We look at hydrogen where we have 2, and oxygen we have 3. Okay, so now that we have it written out, it's obviously not balanced, right? None of these numbers are the same on either side. So let's start working through balancing this equation, okay? And if anyone's just joining in now, I'm putting the attendance in the chat, the link for the attendance in the chat. If you could please just fill that out. Thank you. So, um, the general rule that I use is typically you want to leave your hydrogens and oxygens last to balance. So let's look at carbon first, right? So I have 8 on my reactant side versus just 1 on my product side. So how can I get 8 carbons on the product side? I can place a coefficient of 8 in front of the CO2, in front of the CO2, right? So now how is that going to change my tally of elements? So if you guys remember from like second, probably like third grade math, the distributive property of multiplication, right? This 8, it multiplies to the carbon. It also multiplies here to the oxygen. So now I need to change, update my tally. So now I have 8 carbons. 8 times 2 is 16 plus 1 here. Now we have 17 oxygens. Okay, now let's look at, so the carbons are equal, right? 8 and 8, that's good, but the H's and O's are not, right? So now let's deal with the hydrogen. So I have 18 on the left side and I have 2 on the right side, right? What number could I multiply to 2 So yeah, what number could I multiply by 2 to get that to 18? I can use 9, right? Because 9 times 2 is 18. So if I put a 9, coefficient of 9 in front of the water, that changes my H to 18, but it also changes my oxygen, right? Because we have oxygen there. So we have to count that again, right? So here we had 8 times 2, 16, plus now we have 9, right? This is 9 times 1. So now we should have 25 oxygens. All right, so we're getting there. So carbons are equal, 8 and 8. Hydrogens are equal, 18 and 18, but the oxygens are not. We have 2 on the reactant side. We have 25 here on the product side, right? So what can we do to multiply to get to 25? Right? So let's look at what we have to work with, right? On the reactant side here, we have O2, right? So we have this fixed subscript of 2. You cannot ever change the subscript in these chemical reactions, right? So this is what I kind of call like the even odd problem, right? You have a fixed even number that you have to multiply in order to get to an odd number, right? Um, no whole number or integer can be multiplied by 2 to get to 25, right? So we have to use a decimal in order to get to 25. Okay. So think what number gets us closest to 25 by multiplying by 2, right? So if we do 12 times 2 is 24. Okay, that's almost at 25. 13 times 2 is 26, right? So we want something in the middle between 24 and 26, right? So if I multiply oxygen O2, we use 12.5. 12.5 times 2 is 25, right? So now that'll give me 25 oxygens, and our number of elements on each side is now balanced. Okay. Now, is this my final answer? Can I leave the balanced equation like this? And the answer hopefully is no, right? Because these coefficients, they must be whole numbers. You cannot have any decimals, you cannot have any fractions. So I have a decimal with a zero point 0.5, right? And I want to cancel that zero point 0.5 out. So how can I do that? To get rid of that zero point 0.5, we're going to multiply each term in the equation by 2 in order to get rid of that decimal. Okay, so now my equation, I'm going to move this aside. Right, so the whole purpose of doing this multiplication of 2 is to get rid of that decimal. Our coefficients, our numbers in front of these chemical species, they must always be whole numbers, okay? So that's why this 12.5 here is no good. So if I multiply everything by 2 here, what is my balanced equation going to be? So I'm going to have now 2 C8H18, 12.5 times 2 was 25, so now I'll have a coefficient of 25 in front of the oxygen. We go to the product side, 8 times 2 is 16, so we'll have 16 CO2. And I'll write this on the bottom. I'm running out of space. We'll have 18 in front of the water. Okay. And even though we, you know, stepped it up by a factor of 2, the equation here is still balanced. Right? If you want to look at the carbon, 2 times 8 is 16. Right? On the product side, how many do I have of carbon? I've got 16, right? For the hydrogens, right? 2 times 12 is 24. Um, 2. Yeah, right. Um, I have 24 here. 18. No, this is wrong. 16 plus 18. Yeah, no, this is good. Um, it's 18 times 2. Oh, it's what I'm sorry, I messed this up. It's H18, not H12, right? 18, so there we go. Right, 18 times 2 is 36, and here we have 18 times 2. And the oxygens, they'll add up to 50, right? 25 times 2 plus 16 times 2 plus 18. Okay, so any questions on that combustion reaction there? So this one here, this is your final answer. Okay, any questions about number one there? Okay. Okay. So number two that says ammonia is synthesized industrially through the Haber process. Ammonia is a common ingredient in cleaning products such as window cleaner. Determine the sum of the stoichiometric coefficients. Okay, so we have N2 plus H2 gives you NH3. So this equation is not balanced, right? So let's start with balancing the nitrogens first. I have two here versus just one here. So if I put a 2 in front of NH3, that gives me two N's, and now it gives me six H's. Okay, so the nitrogens are equal, right? But hydrogens are not. I have six here and I have two here. So how can I get to six? I can multiply this by three. And now the equation is balanced. Okay, so I'm asking for you to determine the sum of the stoichiometric coefficients, right? You might remember from your early math classes, the word sum means addition, right? So I'm going to just add all of the coefficients that we have here, right? So 1 plus 3 plus 2, the sum of your coefficients is going to be equal to 6. Okay. Um, I'll give you a minute or two to work through number three. So balance this chemical equation, and then we'll go over it in a couple of moments. All right, so we'll start going over number three. So balancing this equation. So we have platinum, chlorine, xenon, and fluorine, right? So let's take our initial count on the reactant side. So platinum, we have one, chlorine, we have four, xenon, we have just one, and then fluorine, we have two. On the product side, platinum, we have one, chlorine, we have one, xenon is one, fluorine, we have seven of them. Okay, so let's go ahead and balance this. Um, and there's like no rule that says like you have to start balancing with a certain element, right? You could start with whatever you want. You're eventually going to get to an answer. But here I would start with balancing the chlorine. So I have four on the left side versus just one on the right side. So let's put a four in front of the CLF, right? So that gives me four chlorines, but that also changes my number of fluorine, right? So I had six here. Now I have four. So now we have a total of 10 fluorines on the product side. Okay, so let's look. Platinum is equal, chlorine is equal, xenon is equal. Now the fluorine is not, right? On the left side, I have two, right side, I have 10. So this is the only place we have fluorine, right? So we have to put a coefficient in front of XEF2 to get 10 fluorines. So we could put a 5 out there. Now that gives me 5 xenon and 10 chlorines, right? Now by doing that, I disrupted my number of xenon, right? Now I have 5 on my left side. On my right side, I have 1. Luckily, though, xenon is all by itself here, right? So just a coefficient of 5 will do the job. Okay, and now we have a balanced equation. Okay, any questions with 3 there? All right, and if you guys have questions as I'm going, just feel free to unmute and stop me, okay? Um, Number 4, so consider the formation of water. So here we have hydrogen with oxygen giving us water. What does this double arrow represent? Does anybody remember what this double-sided reaction arrow means? So this double arrow, it means that this chemical reaction is happening in equilibrium. Equilibrium. Okay, all that really means is that this reaction is going both in the forward direction, so from the reactants to the products, and it's also going in the backwards direction from the product back to the reactants. So it can go in the forward direction, and it can also go backwards. Okay. That's really all you need to know for equilibrium. It's a very small point in this class, but when you get to chemistry 2, you'll talk a lot about equilibrium. Okay. Any questions on the first page before we move on? All right. Number 5, this says true or false. When balancing chemical equations, you can alter the subscripts. We know that is false. The only thing we can change, remember, we can only change the coefficients, not the subscripts. Right, so remember the coefficient is the number that goes in front of the chemical, whereas a subscript is that little small number, right? Now, the reason for this is because if you change the subscript, you're changing the chemical, right? So, um, for example, H2O is water, right? We all drink water every day. It's perfectly safe for us to consume, right? But imagine I put a 2 in front of imagine I give the O a subscript of 2, and I make it H2O2, right? This is no longer water, right? H2O2, this is hydrogen peroxide. So changing the subscript changes the entire chemical, which you can't do. So you're only able to change the coefficient that goes in front of the chemical species. Okay, number six, talking about electrolytes. So electrolytes, I'm sure you guys have heard about electrolytes like in sports drinks, right? Like Gatorade, liquid IV, all that type of stuff. So electrolytes are ionic compounds and they may conduct electricity in water. So an ionic compound we know is made up of a metal and a nonmetal, right? So something like sodium chloride. So what's so important about these ionic compounds is that when an ionic compound is in solution, when it's in water, it breaks apart into its individual ions. So if I have a beaker of water here and I put sodium chloride into it, it breaks into the sodium ion and the chloride ion. Okay, and these charged particles are able to conduct electricity in a solution. So that's why like you hear of electrolytes, in us because um when you think of like the brain, right? The brain uses electrical signals to communicate, right? So we have to have an, adequate amount of salts in order for that electricity to occur, okay? And the reason that our bodies are able to conduct electricity is because we're pretty much just like a giant aqueous solution, right? We're 70% of water. So this is why electrolytes are important to us. Okay. All right. Number seven, this says, which of the following compounds would be soluble in water? Um, I'm going to give you a minute to work through these. There are three correct answers here, so it's a multiple select. Okay, and to help you with this, at the end of this worksheet, I attached the solubility table. So take a few minutes to look over that, and then we'll go over the answer. All right, how we doing? Anybody have any answers for number seven? So which will be soluble in water? Okay, so our answers here should be A, B, and E. These will be soluble in water. Oh, good. So first two and then also E, right? Um, so really this just comes from looking at the chart and reading it, right? So um see we had strontium hydroxide, sodium nitrate, and lithium sulfide. Right? So it's really just a matter of reading the chart. Okay, so here this first chart contains the soluble compounds. So if it's soluble, it will dissolve in water. It will be soluble in water. The insoluble compounds will not dissolve in water. They will form a solid precipitate. Okay. And so just where people get mixed up is just these exceptions, right? Just make sure you look for the exceptions. So strontium hydroxide, right? Let's look here. So for the insoluble compounds, most hydroxides are insoluble. However, strontium hydroxide is an exception, right? So strontium hydroxide will be soluble. Sodium nitrate, let's look at that. So soluble compounds, almost all salts of sodium and salts of nitrate. So we know sodium nitrate will be soluble. And then for lithium sulfide, we look back down here with the insoluble compounds, right? So most salts of sulfide are insoluble. However, except if you have an alkali metal cation. And we know sodium is an alkali metal cation because it's in group one. So it is an exception. It will be soluble. Okay. So any questions on number seven there? All right. Let's look at number eight now, where we're going to get into writing net ionic equations. Okay. So in writing a net ionic equation, what you're doing is you're representing the formation of a solid precipitate that happens in a precipitation reaction. Okay. So the three steps that go along with it, so just so you know what these letters represent, BE, this is where we write the balanced equation. CIE, this is where we write the complete ionic equation. And then NIE is the last step where we write the net ionic equation. Okay, so this problem says that iron 3 nitrate is added to sodium carbonate, and we have to write this equation. So I give you iron 3 nitrate, I give you sodium carbonate, right? I'm only giving you the reactants to this equation, right? So in this chapter, going over chemical reactions, you are responsible for being able to write chemical equations, predict products, as well as classify the different types of chemical reactions. So how do we write iron 3 nitrate and how do we write sodium carbonate? So iron 3 nitrate is going to be FeNO3 for iron nitrate plus sodium carbonate, which is Na2CO3 Okay, definitely something I should have mentioned earlier. Definitely for this exam, you should know your polyatomic ions by now. So, um, you know, being able to write this comes from having knowledge of the polyatomic ions and knowing their charge as well, right? Because you need to know the charge in order to write a proper, a proper chemical formula. Okay, so here are the reactants, iron nitrate and sodium carbonate, and we have to figure out the products. Okay, so we precipitation reactions undergo what we call double displacement, also known as metathesis reactions. So double displacement, it two things will displace each other, right? So what happens in double displacement, also known as metathesis reaction, is that the cations and anions will swap with each other. Okay, so I also like to say that the outsides with the outsides and insides with the insides, right? So if you watch, remember the cations and anions are gonna flip with each other. They're gonna swap, right? So iron will iron's gonna go with carbonate, right? Outside with outside, right? This cation swaps with this anion, and then again, this cation with this anion, the insides with the insides. Okay, so now for the products, how do we write these as chemical formulas? So now we're combining iron 3 plus with carbonate 2 minus. So how do you write that? That is going to be Fe2 CO3 3 plus we're combining sodium and nitrate. They each have sodium has a +1 charge, nitrate is -1, right? So this is just going to be NaNO3. Okay. Next, you have to balance the chemical equation, right? Just by looking at it, we can tell it is not balanced. So let's go ahead and balance that. Let's balance our irons first. So let's say if I put a 2 in front of the iron nitrate, now that gives me 6 nitrate. So I have 2 irons and now I have 6 nitrates. So let's put a 6 in front of the sodium nitrate. So I have 6 nitrates. Now I have 6 sodiums on the right side. I want to have 6 sodium on the left side, so we can put a 3 here. And now it's a balanced equation. Now the next step is assigning the states of matter to the products. So here you will have to use your solubility chart. Okay, you will be provided with a solubility chart on the exam. You don't have to memorize the solubility rules. So we're going to look at the iron carbonate, figure out what state of matter that will be, and then also same for the sodium nitrate. So you consult your solubility chart, you'll see that sodium nitrate is soluble. So because it's soluble, we know it's gonna dissolve in water, right? So this is gonna be aqueous, whereas the iron carbonate is insoluble. It'll form a solid precipitate, so iron carbonate is solid. Okay, any questions from the first step here? Just writing the balanced equation. All right, so yes, so the for precipitation reactions, the reactants, they're always going to be aqueous. So good question. I'll actually let me just write that in. Okay. Next step is writing the complete ionic equation. in writing the complete ionic equation, you are going to ionize all of the aqueous species. Okay. So that means everything that is aqueous, we have to break it apart into its respective ions. So we're going to start here with our first reactant, the iron nitrate. So writing this out, you need to pay attention to any coefficients and any subscripts that you have. Okay. So we're starting here with the iron nitrate. Okay. We're going to have two irons. And remembering the problem is I said it was iron 3, right? So we know iron has a 3 plus charge. Okay. Then we move over to the nitrate. Now, this is why I was saying to pay attention to both the subscripts and the coefficients, right? You have a subscript of 3 for nitrate and a coefficient of 2 in front of the whole chemical formula, right? So these will multiply to each other. So we're going to have 6NO3 minus, and that takes care of our first reactant. Now we move to sodium carbonate, right? So we're going to have 6Na plus 1, and we'll have 3 carbonates, and we know carbonate is -2. Okay, so that deals with our second reaction then. Now we move to the product side, right? And remember, when I said when writing the complete ionic equation, we are only ionizing the aqueous species. So the iron carbonate is solid, right? So we cannot ionize that. So we're gonna just write it exactly as it is. You're gonna keep it together. Then we move on to the sodium nitrate, which is soluble, right? It's aqueous, so we can ionize that as well. So we'll have 6 sodium plus and 6 nitrate minus. Okay, any questions up to this point? Does anybody know what step comes next after writing out the full complete ionic equation? Good. So now we can cancel out our spectator ions. Okay, so spectator ions are ions that show up on both sides of the equation here, right? So what is a spectator? The 6Na plus as well as the nitrate. Okay. After that, you move to your last step in writing the net ionic equation, where you are going to you're going to copy everything except for the spectator ions. So what are we left with? We have 2 Fe3 plus aqueous plus 3 carbonate, and that yields you solid iron 3 carbonate. Okay. Now notice that so definitely make sure you are able to identify spectator ions. Okay, you will be asked about like you'll be given a you'll see in a minute I have a problem where you're asked to like select what the spectator ions are. So just really make sure you know what the spectator ions are. Okay, you will be asked about that on the exam. And the reason they're called spectator ions is because notice they don't show up in our final equation, right? Right? If you think like spectator ions, right? It's kind of in the name. If you're at a sporting event, right? Say you're at a baseball game and you're a spectator, are you're not contributing anything to the game, right? You're just sitting there and watching. So it's the same idea here. The spectator ions do not contribute anything to the overall reaction. They're just sitting there and watching and hanging out. Okay. So any questions with number 8 in terms of like writing the equation, finding the products, any of that? All right. So moving on to page 3 here. So this says ammonium carbonate reacts with magnesium chloride. Select all the spectator ions of the reaction. So this is pretty much what I was just talking about. Um, so we have to write out this equation, okay? So we have ammonium carbonate, which we know is NH4 2 CO3 plus magnesium chloride, which is MgCl2. Again, we have to predict the products, and we know this is a metathesis or a double displacement reaction, right? So again, your cations and anions are going to swap with each other. So what are my products? I'm gonna have ammonium chloride, so NH4Cl, plus magnesium carbonate. Okay, and just like the last one, now we have to balance the equation. So I'll put a coefficient of 2 in front of the ammonium chloride, and that's it. That balances the equation. Okay. Next from here, you have to consult your solubility table and figure out which of the products will be soluble, which of the products will be insoluble. So you look at your chart. Ammonium chloride is soluble, so it's aqueous. Magnesium carbonate is insoluble, so it's a solid. Okay, and now we can proceed with writing the complete ionic equation. So this was the first step here of the balanced equation. So now we go into the complete ionic equation, where again we're going to ionize all of the aqueous species. And remember that the reactants are aqueous, right? So we go ahead, we ionize all of our aqueous species. So we have two ammoniums, and we just have one carbonate. Then we move to MgCl2, so we have Mg2 plus, and then we have 2Cl minus. Right, we move to the products now. We're gonna have 2NH4 plus, 2Cl minus, and then the solid magnesium carbonate. Remember, we don't ionize that. So let me just move this because I'm running out of space. Right, and from here we can answer the problem, right? Ammonium is a spectator, chloride is a spectator, so the answers are going to be C and E. Okay, any questions with number 9? All right. Um, for 10 here, What states of matter do we not ionize when writing net ionic equations? You do not ionize solids, which we already discussed, and also liquids. You do not ionize. So just make sure you know that. All right. Um, Number 11, predict the products and balance these reactions. So we'll go through this quickly again. Um, so finding the products, again, these are double displacement reactions, right? So the K will go with the N, the Ca will go with the Cl. So what do we have? We're combining now potassium with the nitride, right? So potassium is +1, nitrogen is -3. So to write that formula, it's going to be K3N, and then combining calcium and chloride. Calcium is 2 plus, chloride is 1 minus, right? So you're going to get CaCl2, and then you have to balance the equation. So you will get a 6 in front of the KCl, a 2 in front of K3N, and then a 3 in front of the calcium chloride. Okay, everybody good with that? Um, I'm gonna skip part B just because I think we have done that a couple times by now. So now let's get into talking about acids and bases. So number 12, I ask you to list all the strong acids and strong bases. So there are 7 strong acids, there are 5 strong bases, and you are responsible for memorizing all of the strong acids and strong bases as well as knowing their chemical formulas. Okay, so for the strong acids, I'll write them out first and then we'll talk about them. So sulfuric acid, we have hydroiodic acid, hydrobromic acid, we have nitric acid, hydrochloric acid, and then we have perchloric acid and chloric acid. So these are the 7 strong acids you must memorize. And then the strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, and then barium hydroxide. Okay, so um, what characterizes an acid or a base as strong? And it's got to do with how it acts in solution. So you need to know that strong acids and strong bases will fully ionize in a solution, whereas something that is a weak acid or a weak base is only going to partially ionize in a solution. Okay. So make sure you have these memorized, okay? And there is a helpful mnemonic that helps you memorize the strong acids, which I'll write for you, and it goes in the order in which that I wrote these strong acids out. Okay, so remember our strong acids, so we have sulfuric acid, hydroiodic acid, hydrobromic acid, nitric acid, hydrochloric acid, which is this is actually your stomach acid as well. Then you have perchloric acid and chloric acid. So the saying for the strong acids that I always teach my students So it goes like this. So it goes, so I brought no clean cloth clothes. And so this little mnemonic, it follows the order of the anions of these acids, right? So is for the sulfuric, right? I for hydriodic, brought, right? And it goes on. So you can use that to memorize the strong acids. Okay, another way that you can identify an acid, they all have the H in front, right? Now, looking at the strong bases, you notice they all have the polyatomic ion of the hydroxide ion, right? And it's mainly the group 1 and 2 metals, right? So we have lithium, sodium, potassium, right? And they have the hydroxide with them. Okay, so any questions about strong acids, strong bases? Just make sure that if you see an acid, if it's not part of this strong list, then the acid is going to be weak. Okay, so just make sure you know that. All right, number 13, this says true or false, weak acids fully ionize in water, and we know that is false. Weak acids we know will partially ionize, whereas strong acids will fully ionize. Okay, any questions on page 3 before we move on? All right, so using this idea of the dissociation of strong acids, strong bases, weak acids, weak bases in solution, I want you to look at number 14. So this says that hydrofluoric acid is added to sodium hydroxide. Write the net ionic equation for this reaction. So I'll give you like 4 to 5 minutes to think about it, get it started, and then I'll start to go through it. All right, so let's start to look at 14. So I tell you that hydrofluoric acid is added to sodium hydroxide and to write the net ionic equation. So again, here I only give you the reactants, right? We have HF, hydrofluoric acid, and NaOH for sodium hydroxide. Um, you should know that the products of an acid-base reaction are two things. It's a water and a salt, right? And you can also get that because for the most part, these reactions also follow that metathesis, right? H with OH, that gives you H2O. And what's our salt? Well, actually, let me write the states of matter. So our reactants are aqueous. H2O, that's liquid. And now what's the salt? It's Na and F, right? Sodium fluoride is my salt. And remember that salt is just a generic term for any ionic compound. Okay, so this is what your equation should look like. So next you check if it's balanced, right? It it already works out that it's already balanced, so that's good. So here's step one of our balanced equation. Now we have to write the complete ionic equation. Okay, so here is where it's really important that you're able to um, identify any strong acids, sorry, you should be able to identify what acids and bases are strong and which are weak, right? Because that's gonna dictate how you write the complete ionic equation, right? So we have hydrofluoric, I did not mean to do that. We have hydrofluoric acid, right? We know this is a weak acid, so it's only going to partially ionize in solution. So that means that we cannot ionize it. We're going to have to write it and keep it together. So we have HF. Sodium hydroxide is a strong base, so that will fully ionize in solution. So we have to ionize that. So we have Na plus, and then we have OH minus. Okay, then we go to the product side where we have liquid water and we have aqueous sodium fluoride. Remember that you do not ionize solids or liquids. So water is a liquid, it cannot be ionized. We're going to just copy it exactly as it is. And then sodium fluoride, we have Na plus and F minus. Okay, from here we can cancel our spectator ions. So here we only have one spectator ion, which is sodium, right? Because here we have F minus, but we do not have F minus on this side. So those cannot cancel out. So finally, for the net ionic equation, we have HF plus hydroxide, and it yields you liquid water and fluoride ion. Okay, any questions on number 14 there? Everybody good with that? All right, so let's do another one. Number 15 says that a chemist performs a neutralization. Sulfuric acid reacts with aqueous aluminum hydroxide in a beaker. Show the net ionic equation for this reaction. So again, here we have to write the chemical equation just from the words, right? So we have sulfuric acid, which we know is H2SO4, and it's reacting here with aluminum hydroxide. So I'm going to give you the products and I'll balance it for you, and then I'll give you a few minutes to work through it. Okay, so here is your equation, and I'll give you a couple minutes to work through this one. And let me know if you have any questions. Any questions so far as you guys are going through this? I'll give you another like 2 minutes maybe, and then I'll go through it. All right, so we can start to go through this problem. So, um, like I said, I wrote out for you the balanced chemical equation. So, sulfuric acid here is reacting with aluminum hydroxide. So you need to um, be able to tell, what the properties of these. So obviously it's an acid-base reaction, right? And you need to be able to know what the relative strength of these acids and bases will be. So sulfuric acid is a strong acid. Aluminum hydroxide is a weak base. Okay, so to write this out, the complete ionic equation, we're going to ionize everything that is strong, and we are not going to ionize anything weak and any liquids, right? So we have sulfuric acid, a strong acid, so we have to ionize this into its respective ions, right? So we're going to break it into H plus and SO4 2 minus. Okay. Make sure you do remember about, right? We have a coefficient and a subscript. So we're going to have 6H plus and 3 sulfate, right? So there's our strong acid ionized here. We move on to our base, which is a weak base, and we know weak bases will only partially ionize, so we're going to keep it together. So just write it exactly as it was shown before. We go to our product side, we have liquid water, so we know we can't ionize that, so keep it together. And then we have aluminum sulfate, which we will ionize, so we're going to have 2 Al3 plus, and then we'll have 3 sulfates. All right. Now from here, we'll cancel our spectators. So um, sulfate is canceled off. And then we are left with 6H plus 2 aluminum hydroxide. And that yields you 6 waters and 2 aluminum ion. So Al3 plus. And that's your final answer. Okay, any questions on number 15? Okay, moving on. Sorry. Why can't you ionize aluminum hydroxide? Because aluminum hydroxide is a weak base. So you cannot ionize anything that is weak. Okay, does that make some sense? All right. Moving on to page 5 here. Um, so I give you phosphoric acid, H3PO4. Is it a monoprotic, diprotic, or triprotic acid? This is a triprotic acid. And you know it's triprotic because it has 3 hydrogens. All right, number 17. So now we're going to get into oxidation reduction reactions. So this says, consider the following redox reactions. For each, label which species is oxidized, which is reduced, and which are the oxidizing and reducing agents. Okay. Um, so let's go through part A together, and then I'll give you guys some time to work on the rest of them. So here I have solid magnesium reacting with hydrochloric acid, and it gives me magnesium chloride and hydrogen gas. So, redox reactions, the significance about redox reactions is that they are um, essentially redox reactions. We are shuttling electrons. So we're gaining electrons, we're losing electrons. Okay. Why redox reactions are so important is because since we are transferring electrons, we're able to make energy from that. Okay. So redox reactions, this is like the science behind how batteries work and also how your own cells make energy, right? The mitochondria in your cells, when they go through the Krebs cycle and the electron transport chain, they are doing redox reactions and transferring electrons to make energy. Okay. So in order to do redox reactions, you have to be able to assign the proper oxidation number to all of the species in the chemical reaction. Okay. So hopefully you remember from the lecture video, there's like a long list of oxidation state rules. You must memorize all of those rules to be able to solve these problems. Okay, so here we have magnesium, right? So we have to assign the oxidation number of magnesium. Okay, so you should recall that when you have a free element, the oxidation number of a free element is zero. So magnesium here, zero. So now we have HCl, okay? So um, we have chlorine, which is a halogen, right? And we know that the halogens have a oxidation number of -1. So chlorine is -1. So that means that hydrogen should be what? It should be +1, right? And you know it should be +1 because HCl is a neutral compound, right? So another thing you should know is that um, the sum of the oxidation numbers has to equal the overall charge for that compound, right? So this is neutral, right? It means it has a charge of zero. So that means that the sum of the oxidation numbers, when you add them up, should equal to zero. So +1 plus -1 is zero, right? So now let's move to the product side with magnesium chloride. So again, we have chlorine, which is -1, but we have two of them, right? So we have -1 times 2, which is -2. And overall, these have to equal to zero. So that means that magnesium should be a +2, +2. Okay. Then we have hydrogen gas. Remember H2? This is the elemental form of hydrogen because it's one of the diatomic elements. And again, when you have a free element, the oxidation number is zero. So H2 is zero. All right, so once you complete that first step of assigning the oxidation numbers, then you can go ahead and compare both sides and determine what's oxidized, what's reduced. Okay, so um, let's look here at the magnesium first, right? So I need to compare how magnesium is changing from one side to the other side. So magnesium starts at zero and it goes to a +2, right? So going from zero to +2, that number is getting more positive, right? It's getting more positive, right? So what's happening to the electrons if it is getting more positive? So remember, I should have started with this actually, but you might remember from the lecture video this acronym oil rig. So oxidation is the loss of electrons. Reduction is the gain of electrons. Okay, so going back to magnesium, right? It's going from 0 to +2, right? That's getting more positive, right? If you think of like the number line, it's getting more towards the positive end of the number line, right? If we're getting more positive, are we going to be gaining electrons or losing electrons? And it makes sense that we're going to be losing electrons if we're getting more positive, right? Electrons, remember, are negatively charged. So if we're getting more positive, we're going to be losing those negative particles, okay? So we're getting more positive, right? We are losing electrons. What do we call the loss of electrons? That is oxidation. So magnesium here is oxidized. Oxi, I always spell this wrong. Oxidized. Okay. Because it is oxidized, that will also make it the reducing agent. And I'll explain that part at the end. So now let's look at what else we can compare. Let's look at the hydrogen, right? Hydrogen in HCl goes from +1 to 0 in H2 on the product side, right? So going from a +1 to 0 is getting more negative, right? So if we're getting more negative, it makes sense that we are gaining electrons, and we know that the gain of electrons is called reduction. So hydrochloric acid is reduced. That also will make it the oxidizing agent. Okay, so you notice that like the agent part is always opposite of what's happening, right? So why that is, right? So remember I said here we're transferring electrons in these redox reactions, right? So um take for example the hydrochloric acid, right? It was reduced, right? We said it was undergoing reduction, so it was gaining electrons, right? So whatever is reduced becomes the oxidizing agent because, right, it's being reduced, it's gaining electrons. Those electrons are not just coming out of thin air, right? It's stealing electrons from somewhere else. So because HCl is being reduced, it's the oxidizing agent because it causes something else to become oxidized, right? It's caused for the electrons in magnesium to be transferred to the HCl, right? If you look at the magnesium, right? Magnesium was oxidized. It is the reducing agent because it caused something else to become reduced, right? Magnesium was oxidized, it lost electrons, and those electrons can't just like float in free space. They have to go somewhere. So because magnesium was oxidized, it caused for something else to become reduced, right? So just know that they're like flip-flop like that, okay? So any questions on part A there? On part A for 17? All right, so I'll give you guys a couple minutes now to work on parts B and C. Um, Maybe take till like 4:40-ish, and then I will go over it. And just shout out if you have any questions. All right, so let's start to go through this. So part B, here we have the permanganate ion reacting with the oxalate ion. Okay, so we need to figure out, again, what's oxidized, what's reduced, and what are the oxidizing and reducing agents. Okay, so um, in part B, you may have run into a problem in which you probably came across an element in which you don't have the rule for the oxidation number, right? So looking at permanganate here, we know that the oxidation number of oxygen usually is -2, but the manganese, the Mn, can have it can have different oxidation numbers, right? So you're gonna see we have to do some math in order to figure out what the oxidation number of Mn is. Okay, so for MnO4, again, we know that oxygen is -2, right? So Mn, I don't know, right? So we kind of have to do some algebra to figure this out. So Mn, I don't know, is going to be X plus oxygen, which we know is -2 times 4. And we're going to set the equation equal to -1. Again, because the sum of the oxidation numbers has to equal your overall charge, right? So we just do a little bit of math here, right? So we end up with X plus -8 is equal to -1. Bring the 8 to the other side, and X is equal to +7. So manganese is +7, oxygen is -2 times 4. Okay, next we move over to oxalate, where again, we know the rule for oxygen, but we don't know the rule for carbon. So we have to figure out what carbon is. Okay, now notice we have two carbons, right? So carbon, we'll write it as 2x plus -2 times 4 equal to -2, right? So 2x plus -8 is equal to -2. Bring the 8 to the other side. 2x is equal to +6. Solving for x, divide both sides by 2. X is equal to +3. So carbon is +3, oxygen is -2. Okay, now we go to the product side. We have MnO2. So again, we have to figure out what Mn is. So x plus -2 times 2 is equal to 0. So we know x here is equal to +4. So Mn is +4, O is -2. Then finally we have the carbonate ion. And again, here we have to figure out what carbon is, right? So we have one carbon. So x plus -6 is equal to -2. Bring the 6 over. So X is equal to +4. So the oxidation number of carbon is +4 and oxygen is still -2. Okay. Any questions on how I figured out the unknown oxidation number there? Okay. So now that we did that, I'm going to erase this math so we can answer the question. All right, so now we're going to compare both sides, right? So just like the last one, this one was a little more difficult because we had to figure out an unknown, right? But that was just some basic algebra to get there, and now we can deal with comparing our oxidation numbers, right? So you look at the manganese and permanganate, right? Plus 7 here. On the other side, the manganese is plus 4. So let's compare those. So going from positive 7 to positive 4, it's getting more negative, right? It's getting closer to the negative side of the number line, right? So if it's getting more negative, it's going to be gaining electrons. So we know this is reduction. And it's the permanganate, the MnO4 minus, is also going to be the reducing agent. I'm sorry, the oxidizing agent. Right? So it's reduced, and it's also the oxidizing agent. Next, you want to compare the carbon, right? So carbon goes from positive 3 to positive 4. That is getting more positive, right? If it's getting more positive, we're losing electrons. So what do we call the loss of electrons? That is oxidation. So oxalate is oxidized, and it is also the reducing agent. Okay, so just um the way you would give your response, you're not responding to the single element, you're responding to the whole thing. So you would say permanganate MnO4 minus is reduced, and it's the oxidizing agent. And then you would say oxalate, so C2O4 minus, sorry, 2 minus. It's oxidized, and because it's oxidized, it operates as the reducing agent. Okay, so any questions on part B? All right, finally, part C here. Um, Here I have potassium permanganate reacting with ethanol. All right, so um, let's assign the oxidation numbers to everything here, right? So um, potassium is an alkali metal. So the nice thing about this is that the alkali and alkaline earth metals, their oxidation number is usually just going to be their charge. So K is plus 1. Mn, manganese, we have to figure out. So that's X. And oxygen we know is negative 2 times 4, right? So 1 plus X plus negative 8, set it equal to 0. Okay. How do we solve this? Well, we have a positive 1 and a negative 8, so we can combine like terms, right? So we can simplify this and say that X plus negative 7 is equal to 0. Right, we solve for X, bring that 7 to the other side. So X is equal to positive 7. So potassium is plus 1, manganese is plus 7, and then oxygen is negative 2. Okay, now we move to our other reactant, the ethanol. Um, and so a an easy, to make your life a little bit easier here is when you see a polyatomic ion, you can just group it together and give it its charge. So we know we have OH, which is hydroxide, right? We can just say that whole thing is negative 1, right? So um, we know what H is. We have to figure out what carbon is. So again, we're going to write an equation for that. So we have 2x plus 5 plus -1 equals 0. We can combine these. So we'll say 2x plus 4 is equal to 0. Bring the 4 over. 2x is equal to -4. Solve for x equals -2. So carbon is -2, hydrogen is +1, and the OH hydroxide is -1. Okay, then we move to the product side. I have Mn2 plus, and this is easy enough because when you have a monatomic ion, the oxidation number is just the charge of the ion, right? So Mn is just going to be 2 plus. Now again, in C2H4O, we have to figure out what carbon is. So 2x plus 4 plus -2 is equal to 0. So we just solve from here. Um, it works out that x here is equal to -1. So carbon's -1, H is +1, O is -2. And then we have K plus, so this oxidation number is just +1. Okay, any questions about solving for the unknowns here? All right, so now we can make our comparisons and figure out what's oxidized, what's reduced, right? So let's look at the manganese here in KMnO4, right? So manganese goes from +7 to +2. That is getting more negative, right? So more negative, it's gaining electrons. So this is going to be reduced. That also makes it the oxidizing agent. And then carbon here, going from -2 to -1, that's getting more positive. Getting more positive, we're going to be losing electrons. So the ethanol is oxidized, and then it's also the reducing agent. Okay, any questions on how we did that? Okay. So 18 is a quick one. Reduction is a decrease in oxidation number, whereas oxidation is going to be an increase in oxidation number, right? And you can kind of see that here. Anything that was reduced, right? The Mn, right? It was reduced. It decreased in oxidation number. It went from a +7 to a +4, right? And same thing with oxidation, it increases the number. It goes from +3 to +4. All right, so number 19 says to assign the oxidation numbers to all the atoms in the sulfite ion. So does anybody know what sulfite is? What's the formula and charge for that? So we know sulfite is SO3 2 minus. So we know what oxygen is. We have to figure out what sulfur is. So we have X plus -2 times 3 equals -2. So X plus -6 is equal to -2. Bring that 6 over. And X here. So X is equal to positive 4. So sulfur is plus 4, oxygen negative 2. Number 20 is pretty much asking the same thing. So determine the oxidation states for each element in arsenous acid. So so let's see, we know H, we know O, we don't know AS. So we have positive 1 times 3 for H plus X for AS plus negative 2 times 3 for the O equals 0. So we have 3 plus X plus negative 6 equals 0. Um, we can combine these terms, right? So we have X plus negative 3 equals 0. Bring the 3 over. X is equal to positive 3. So H is plus 1. AS is positive 3, and then O is negative 2. And then the last problem here, the oxidation state of chromium in K2Cr2O7. So K we know, Cr we don't, and O we know. So we have plus 1 times 2 plus 2x plus negative 2 times 7 equals 0. So then we do 2 plus 2x plus negative 14 is equal to 0. We can combine the 2 and the negative 14, right? 2x plus negative 12 equals 0. Bring that over. So 2x is equal to positive 12. Divide by 2. And x is equal to positive 6. So your answer is going to be D. Okay. So that's pretty much everything you need to know for Monday's exam. Any questions about any topics from today? All right, so if there's no questions, you guys are all good to go. Have a great weekend and good luck on the exam on Monday. Hey, you're welcome, guys. Bye bye.